Senior Software Engineer of AI and Systems at Jabra.
Awesome. Thank you so much for hanging around, especially since it's the last talk of the 3D event. So my name is Anuj, and I work at Jabra in the Intelligent Video Systems group. And today we'll be discussing about some techniques around model compression. So here's our plan of attack. We'll start with a basic introduction, looking at basic techniques about model compression, what it is, what are the basic techniques, try to understand some basic key metrics, define that, because otherwise how are we going to even compare that? How do these model compression techniques even help us and where? And then we'll end up with a case study at how at Jabra we used model compression for deploying models at the very edge in all our video collaboration devices that are present in the market right now. And then we'll summarize some best practices and hopefully leave time for the QA. So let's get started. So traditionally, models have been increasing in size. Everybody knows transformers came out in 2017. Model size was pretty kind of big, 65 million parameters. Since then, nowadays, we are at what, 100 billion or even more than that? So, of course, traditionally, models needed to be trained in the cloud, and there were very less number of edge devices. So that means you could easily make some API calls, and you could do the inference there. But as more and more number of edge devices started shipping out, more amount of compute is available on your edge devices, plus more amount of data is being generated at the edge. So it definitely makes sense to do more amount of compute there. For example, if you are doing some kind of health metrics on your Apple Watch, it doesn't make sense to send that data to the cloud and wait half an hour to figure out what your heart rate was. You want to see it right away. So that's one part of it. So now inference is coming more to the edge. But at the same time, for training these models, it consumes a lot of energy and a lot of carbon dioxide emissions. So looking at our environmental and sustainability goal, I think edge AI is a pretty good thing to go forward with, because this is only the training cost, but imagine about the inference. You train the model once, you are doing the inference calls, maybe 10,000 API calls per day. So that's going to count a lot more, even as compared to the model training. So just briefly looking at what model compression is. So imagine you have a huge neural network, and ideally we would like to take it down to a very small neural network, which we can easily fit on our edge devices. So we have a smaller model size, faster inference, reduced energy consumption. Sounds really good and easy, right? Not exactly. So here are the challenges in edge AI. You have challenges in terms of latency. You need efficiency. You need availability, because it's on the edge, should be available all the time. And data privacy, which is of utmost importance in nowadays. So for example, in terms of latency, say you have a self-driving car and you have your whole model pipeline deployed on that. Depending upon how fast your self-driving car is going, if your model have too much of latency, your car could end up with an accident. Similarly, on the other end, you have your home assistants, you have smart assistants at home, on your watches, on your phones. They are listening to you all the time for different kind of keywords to stay awake and to respond to you as fast as possible. But you want to do that processing as much as possible on the edge without sending too much data to the cloud for privacy purposes. You don't want to continuously listen to what people are saying, what they are doing, and send everything to the cloud. That's of no use. On the other hand, there is diversity in the kind of hardware that's available. You have CPUs, GPUs, DSPs, specialized deep learning accelerators, and they have their own problems. So in terms of flexibility, you lose flexibility as you go from CPUs to deep learning accelerators. So anyone here who worked on the hardware or who works on the hardware, who provides hardware for the edge AI, will truly understand this, that in 2017 when transformers came out, everyone started asking, when are you going to support transformers on these edge devices? When are you going to start supporting int4 quantization? And those were not supported out of the box on specialized deep learning accelerators. So every hardware vendor had to move around and figure out how can we support this. Everyone till now has been having a second version of their hardware on which they have made some changes to support all the transformer layers. So that's the flexibility. You lose some flexibility there, whereas on day one of the transformers launch, you could easily deploy them or play around with them on your CPUs, GPUs, anywhere else. But in terms of efficiency, you have these specialized accelerators that are truly efficient in terms of power consumptions, whereas in CPUs and GPUs, the power consumption is ideally higher. So what good is model compression and other techniques if we don't define some key metrics on which we can compare them? So here are some basic key metrics looking at hardware and software in conjunction. So we need size reduction, so model size should be reduced. We need accuracy or any other metric depending upon your problem, like object detection, it could be mean average precision. You need the throughput, so amount of number of operations that you can perform on the hardware. Latency, starting from the time your data entered your SoC till you generated the results. And then you look at memory bandwidth, because your ML might be just a small part of the entire system. There are other things at play. You have audio processing, video processing, encoders, decoders, scalars, all those kind of things. So ML needs to work there, but it has to share the same memory bandwidth depending upon your hardware architecture. And then power and energy consumption, because you only have certain amount of power and energy consumption budget, otherwise you reach your thermal limits. So wouldn't it be great if there was some kind of graph or a plot that could actually combine all of these metrics? And that's what exactly the roofline model does. So basically what this explains is basically a graph between the operational intensity of your hardware versus the performance that you get. And you want to be as right of the inflection point as possible. Why? The ceiling here defines your slope, which is the bandwidth that you have, which is the memory bandwidth. But on the right, you want to keep as close as possible to the roof, because you want your hardware to be as much utilized as possible. So if you are on the left side of the optimal operational intensity, that means you have your hardware available. You're processing elements that can perform, say, a single MAC operation, but you are not able to provide the data fast enough, so your hardware is remaining idle. So that's of no use. Whereas on the other side, you are able to fully utilize your memory bandwidth. You are able to provide the data in time, but all the processing elements are being used fully. So that's totally fine. That's what we need. So how does model compression help here? You have reduced amount of off-chip memory accesses. So that in terms reduces the amount of energy consumption, because now you don't have to go to the external memories constantly that consumes a lot of energy. You have better hardware utilization. You increase your throughput and reduce latency. And if you want to run multiple models, and if a model is small enough, you might be able to even run multiple models in parallel now. So quickly looking briefly at what are the certain model compression techniques that we can use. So first on is neural architecture search. So basically you have, say, a set of layers that you want to use in your model. You know that these are the model layers that work totally fine on my hardware. I know my hardware well. I can define that as a search space, maybe do like a generic grid search, or maybe use a reinforcement learning algorithm, and then let the model figure out that what is my optimal architecture design that I want to use. It could be for, say, accuracy versus latency. It could be accuracy versus throughput, or whatever metrics you define. So one of the prominent examples is like MNASnet, where they define what's the convolutional operations that you want to support, what is the maximum kernel size, what is the skip operation that you want to support, and so on and so forth, and then put them into layers and then define blocks based upon that, and you stack the blocks, and you have a network that works optimally. In this, you can also put hardware in the loop, so that you know exactly that whatever latency constraints that you're calculating for your optimal model are for your existing hardware where you want to deploy at the end. And here are just some of the basic numbers on an average, what you can achieve in terms of our key metrics. So you have good numbers across size reduction, throughput, memory bandwidth, 2 to 5x latency reduction, and power efficiency. Next, hardware-aware design, which is very, very important, because you know the hardware, or you either know the software, but the end product is a combination of hardware and software. They both go hand in hand. It's not either of those. So basically what you can do here is, if you know your hardware well, if you know what layers are supported, what's the latency of your layers, or different kind of kernel operations, you can define those layers or choose those layers based upon that. If your hardware has been defined before, then you know what's your memory budget, you know what's your latency budget depending upon the applications. So you can choose the layers accordingly. For example, we know that in convolutional neural networks, mostly the feature maps that are there, most of them have redundant information. So can you reduce the amount of compute there? How can you do that? Maybe reduce the number of redundant features and apply computations only to a set of them and leave the rest of them. So that way you're reducing the amount of compute. Similarly, in case of, say, for example, you want to perform upsampling, which we usually perform using, say, transverse convolutions, which will take certain amount of compute, you could replace them using a depth to space operation, which is a pixel shuffle operation, which is kind of cheaper operation as compared to using any other kind of operations. Similarly, recently one paper came out by Apple, mobile one, where they use tricks like reparameterization tricks, where you can mimic huge convolutional layer with, say, one or multiple smaller layers, where you have reduced number of parameters, reduced number of computations to be done, as compared to one huge layer. So that saves you a lot of time. Although during training, you can still over-parameterize your model to reach the performance that you want, but during inference is where you want to avoid all the layers as much as possible. So you try to do reparameterization, you try to do folding of the operation like batch norm into convolutions and so on and so forth. So using these techniques, they are able to reach around 1 millisecond latency on an iPhone 12 using CoreML. So this is basically a great example of hardware-aware design. Knowledge distillation is another technique where if you have already a huge model that you're starting with, and if you want a smaller model, so basically what we are trying to do here is look at the distribution of the weights of the teacher model and trying to learn from the student that what is the distribution, can you learn this distribution or not. So basically passing the same data as input to both teacher and the student, and then only doing the back propagation through the student so that the student weights are updated but the teacher weights are frozen or intact. One primary example in terms of transformers has been DistilBERT, which is a great example of knowledge distillation from the huge BERT model into very small size BERT models. And these are kind of the numbers that you can achieve on an average for the models, depending upon what kind of model and application you have, using knowledge distillation on the key metrics. Similarly, next thing is pruning. So most of the neural networks are over-parameterized. So that means there is still a lot of scope for model improvement. So till now we did neural architecture search, we made efficient hardware-aware design, we looked at knowledge distillation. So now we have a smaller model. Can we make it more smaller? Yes. It's still over-parameterized. You can perform model pruning. So you can prune based upon magnitude pruning, structured versus unstructured pruning, local versus global, and different kind of pruning techniques. So it's basically like cutting off some of the connections and looking at how does it affect my model accuracy. Because at the end of the day, it's a trade-off between my accuracy and the model size. I want to balance both of them. Usually in CNNs, the model pruning is kind of fine to use. It has been used for a long time. But with transformers, it gets a little bit tricky because you can prune on two places. One is your multi-head self-attention layer, and second is your feed-forward layer that's there. But with the attention layer, it gets tricky because it's learning all the attentions and all the values that it's learning is pretty sensitive. So even the smallest of the values could be pretty important for making a final decision. So that means if you prune a lot, you could be missing those values and they could be turning down to 0 from that smaller value and you lose the entire aspect of it. But if you don't prune it enough, then you end up with a huge layer which might be too heavy for a very small edge device. Another thing you can do here is you can optimize the whole multi-head self-attention layer as well. So as it is, it takes around order n square multiplication operations for just the MHSA. You can take it down to order like a linear time complexity easily if you are careful enough with the design of the MHSA block itself. And these are like on average some numbers that you can get in terms of the key metrics on the hardware. Okay, so we have the model, we pruned it, we have a small enough model, we are happy with the size. What else can we do? It's still having, say, floating point 32, floating point 16 weights. What else can we do? Model quantization. So the weights are there in floating point 32. I can take them down to int 8, int 4, depending upon what my application is. Does my hardware support it or not? What is the advantage of doing this? Basically, if you see on the right the image, so it basically shows the amount of energy that's required for doing operations on 8-bit additions versus a 32-bit multiplication or addition operation. There is a huge difference in energy as well as the relative area cost. So if you have a floating point 32 values, that means it's going to take a lot more amount of memory, which you could have used for adding maybe more compute onto your hardware. So that's a trade-off that you're doing in terms of the quantization aspect. If you have int 8 or int 4 weights, that means you can reduce the amount of memory size that you require on chip, and you can increase your number of processing elements or compute that is there. Similarly, doing quantization for general neural networks like CNNs and all is fine. But again, in transformers, it becomes tricky because in transformers, the activations have outliers that you cannot just leave as it is, because if you leave the outliers as it is, you don't only end up with quantization errors, you actually add up a lot more errors. So what usually people like to do there is take those outliers and put them into a higher precision. So basically, for example, if you have outlier activations, use them into like floating point 16 and keep the weights as int 8. Or maybe otherwise, if your hardware supports it, keep your weights to int 4 and keep your activations at a higher quantization so that you don't lose the entire aspect of it. And there are two prominent ways of doing quantization. Either once you have already trained your model, now you want to quantize it. So use your post-training quantization where you provide your calibration data. You can quantize your model. You can do it using either block quantization or normal quantization. There are so many ways. Other one, which is more prominent and might give you better results, is quantization-aware training. If you know beforehand that what kind of quantization your hardware supports, what kind of quantization do you need, you can actually train your models with the quantization built in so that it knows during forward propagation that these are the weights I'm going to see. So train the model weights accordingly. But during back propagation, the weights will still be in full precision. So otherwise, your gradients might become 0. And on average, these are some of the results that you can get on the key metrics. Cool. So we discussed everything, all the major techniques pretty quickly and briefly. What are the pruning techniques that you can get? But one question that you might have is, okay, we have seen this before, but are these just techniques? We have seen this. Is it just theory, or can you actually apply this into production? So here's the example that I want to show you that we recently applied into production. So imagine that you are an employee, or you are a researcher or engineer working at, say, top 4 financial firms in the world, say, for example. And you might have to do a lot of video call meetings with a lot of your clients. So you might be sitting in a setting where you have different kind of trading information on your screens, or some colleagues sitting by, depending upon if it's your open office condition. Or maybe you are sitting in a meeting room which has, say, some kind of whiteboard which has some kind of stock information or other kind of sensitive information that you don't want it to go out. You don't want the next day stocks to tumble just because you were on a video call and somebody saw some numbers. So that's where having image segmentation that runs on device in super real time helps a lot. And to fully appreciate the complexity of it, again, the ML model is a very small part of the entire system. There is video subsystem, there is audio subsystem, there are scalars at play, and then there is the ML model. But in segmentation, it becomes even trickier because you need to run it at near real time or even faster than that, because otherwise all your segmentation maps are going to blow away. So basically your latency constraints are there. Anywhere between 24 to 30 milliseconds, you have to run it, you have to give the results, otherwise it's of no use. So what's the solution here? Running background segmentation on device, ensuring that only important data is transmitted, which is just you and nothing else. So in terms of that, we know the constraints now. What are our model design goals? It should be efficient, it should be lightweight, needs to run real time. It should be accurate, it should be having a flawless segmentation, otherwise it's of no use. And then it needs to run super real time on the existing hardware. And note that at a certain point of time, there might be more than one models running as well. So you need to take care of that as well. Because usually in cameras that are there for general use for using as a personal camera or meeting rooms, they have other features which might be detecting the people, might be looking at the scenes and analyzing the scenes, might be doing other kind of things in parallel. So that means there are a lot of things that are sharing the memory together, sharing the compute together, and your model needs to fit there and still be real time. And in terms of the outcome for running this on device, you get enhanced data security using during your virtual meetings. So coming back to all the things that we discussed so far and how they connect to us, hardware-aware design. On our hardware, before I joined, hardware was already decided, so I had no choice there. So on hardware, what can you do? So we looked at the hardware, we looked at hardware-aware design first. Space to depth is one thing that we found that if you have a higher input resolution of the image going into the model, based upon hardware, it was having higher latency. So that means the very first thing that we have to do, as soon as you get the input image to your model, scale it down as fast as possible using large kernel sizes or using strides instead of using pooling layers to keep the parameters in check. Second thing we noticed was that using skip connections, actually, for example, in a U-net or U-square net kind of architecture, which is primarily used for segmentation, in terms of going from the encoder to the decoder side, unless you reach the decoder layer where you have to perform the concatenation of the skip layer that you had in the encoder layer, you still have to maintain those activations in memory, because otherwise, how are you going to take that information from the encoder and pass it to the decoder? So that means that's going to add in terms of memory cost as well as in terms of latency cost. So what do you do about that? What we figured out is, like, if you maintain the lower number of channels in those specific layers where you have to perform that skip and concatenate operations, is going to run super fast up to a certain level. Above that level, you incur latency. Using separable convolution didn't provide us any kind of additional advantage, but they do help in reducing your model size. And then, as we mentioned before, in terms of pixel level, pixel shuffle layer, which is performing depth to space, so that helps a lot when you're doing your upsampling in the decoder layers. Next thing, how do we do model training? So we try to use model training using self-supervised learning. We begin with our efficient architecture. We understand our hardware well. We make our own hardware architecture. We start with a self-supervised learning technique where we provided the data without the labels because labeling is costly. So provide as much data as possible without the labels, do the self-supervised learning, and then start doing fine-tuning on the custom data set that we have collected using our cameras. So again, limited by the hardware, we have to quantize our model or do quantization-aware training, and we quantize the model and save it in floating point 16. Hopefully, in some new products, we might be able to do int8 and int4 as well. And then we finally do the model compilation, so converting it to binary, and off it goes. So looking at some of the timings that we have on our hardware, as we mentioned before, skip connections at till concatenations, you have latency, both in terms of saving your intermediate parameters or the activations that you got as output until you reach the decoder layer where you have to concatenate those operations. So that incurs latency for depending upon the layers you are using. Also, looking at the spatial resolution, as we mentioned before, if you have a higher resolution, say for example 512 by 512 RGB image coming as input, you see that as we start increasing the number of channels, the latency starts increasing by a lot on the hardware. Whereas if we take the resolution down as soon as possible, say to 128 by 128 or 64 by 64, as you increase the number of channels, the latency increase is not as drastic as compared to when you have an even higher resolution. So this proves that taking down the image resolution pretty quickly helps a lot. So finally, one comparison of our device actually doing segmentation versus two of the most prominent video collaboration devices. Now, to fully appreciate this, let me tell you the thing. So our model is working on a Jabra Panacast20 camera, which is running these model on device. The model size is somewhere around, say, 900 kilobytes to 1 megabytes. And it's running super real time, and none of your extra data is leaving the device. You can connect your camera to your laptop, and you can confirm that for yourself. On the other hand, for video collaboration devices that everyone uses, depending upon what kind of hardware capabilities you have on your laptops, if they can process the models locally, that's fine. Otherwise, all of your raw video data usually goes to the cloud where they apply super resolution or they apply like background segmentation and all those kind of things. So that basically means your data has already gone out. All your sensitive information is already out in the cloud. Whether they see it or not, we don't know, but it's leaving your computer. That's what we are trying to avoid here. So here's a quick example of how it looks like. So it's kind of pretty comparable, and it's only our first version of the model that we have released recently, and we are still working on making some more improvements on this. But overall, you can see it still does a pretty good job as compared to any of the video collaboration platforms which are running these models on huge GPU clusters versus a very small CNN accelerator having the whole system along with it. So in summary, neural architecture is pretty useful when performance is crucial and manual tuning isn't yielding any kind of desired results. Hardware-aware design is of utmost importance. Understand your hardware. It's not only a software problem, it's a hardware and a software problem. So understand your hardware better. It's very useful when you are deploying models on the edge devices with unique hardware constraints. Knowledge distillation, if you have a huge teacher model that is already available to you, make use of it to create a smaller model where you can learn the same weight distribution. Quantization is very useful when you want to deploy for real-time deployments where you require super fast execution times. So depending upon what your hardware supports, go to int4, int8, whatever your hardware supports, and there will be a trade-off between the model performance and the accuracy. So keep that trade-off in mind. And similarly for pruning, it's ideal for models which have large number of parameters, which is usually the case when you're starting with, because most of the models are over-parameterized. But one thing to note with pruning is that if your hardware supports pruning natively, if your hardware supports sparsity, only then it's of use, because otherwise you will still be multiplying zeros and you won't be seeing any kind of difference in the performance. Thank you. Cool. Any questions?
You gave us an idea of what it's you're running on in terms of hardware, rough memory sizes. What's the rough power for this application? Because the real application power in a normal environment is many, many watts. What do you think you're living at on the camera?
So this Panacast20 camera is basically for your use in office environment or personal environment. So that means basically whatever your laptop USB hub can provide, the whole system runs on that, including audio, video, and the ML system.
Very nice, thank you.
You mentioned language models like BART. Were you doing anything with stuff like Llama 2 as far as compression or quantization? I mean, you probably have to know very much about the architecture to be careful on what you prune or quantize.
Yes. So not on this particular product, but we have other products on which have higher capability in terms of hardware. And that's where we are looking at, not particularly Llama, because we are more focused on the video aspects of things here, as we are a video collaboration group. But we definitely look at those models and look at the core layers, which is the transformer layer, the multi-head self-attention. How can we optimize it even further before we even go to the pruning or quantization layers? So that's where I was giving a hint, where we have been doing internal research and we have been able to reduce the time complexity or the amount of multiplications that are required for a multi-head self-attention from polynomial to a linear time complexity. So those are some kind of things where efficient hardware design comes into play, where you can play around with the neural network, understand that how things work and how can you make it further efficient, so that before even you reach any of the quantization or pruning layer, your model is already optimized, and then you have even more gains on top of it.
Are there papers or a blog talking about that square to linear time frame?
Not yet, but soon we'll publish that. It's still a work in progress.
Okay, thank you.
Thank you.
Time for one more question.
Hi, maybe I missed this. What kind of hardware are you running this on? Or
Yeah, so it's a custom hardware. That's what generally people tell me to say. But it's not like super like new hardware that's available in the market right now. It's a custom hardware that was built into the products, and that has been baked into most of our existing products in the market right now. Yeah, it's really hard to say, but it has like a CNN accelerator built into that, where you can run only like floating point 16 operations. So it's just optimized for that, and you have like the compiler that's provided by the vendor, because we don't make that hardware. It's provided by the vendor. We just use that, create the binaries. We try to optimize as much as possible for the hardware, and that small amount of ML space that has been given to us from the whole rest of the system that's running there, utilizing scalars and everything else. So we just try to optimize for that and utilize that part.
thank you.
Thank you so much, Anuj. I'm sure if there's any more questions, you can catch him in the corridor.
Sure. Thank you so much. Thank you.